The D-level turbine is a simple impulse turbine which consists of nozzle and one row of moving blade. The high pressure steam from boiler is completely expanded in the nozzle. Because of this, there is an enthalpy drop and there is an increase in kinetic energy of the nozzle. High velocity jet, when impinges on the moving blade row, gives the axial thrust as a tangential thrust gives the axial thrust or tangential thrust. Thereby the kinetic energy is converted into mechanical energy. The steam with which it leaves the turbine is at a very high speed. Because of this, the rotational speed of the turbine is very high, approximately 40,000 to 50,000 rpm, and there is a loss of kinetic energy at exist. This loss can be recovered by compounding. The steam will enter from this side and then the steam passes over the symmetrical blade. So this is a symmetrical type of blades and there is a ring of blade. When the steam will pass over here, it gives the axial thrust, it gives the tangential thrust like this one, and thereby the turbine will rotate. This one represents the boiler pressure. The complete expansion takes place in the nozzle and then this leaves at condenser pressure. Because of expansion, the steam velocity will increase in nozzle and it will drop in the moving blade. So the kinetic energy is converted into mechanical energy. Alpha 1 and alpha 2 are the angles made by absolute velocity at inlet and outlet with the plane of moving blades. Beta 1 and beta 2 are the blade angles at inlet and outlet. V1 is the exit velocity of nozzle or inlet velocity to moving blade. V1 is normally obtained using the equation of 2 times delta Hs multiplied by nozzle efficiency, where delta Hs is the isentropic drop in the nozzle. U is called as mean blade velocity. Is usually given by pi d n by 60, where d is the mean diameter of moving blade. So this is a cross-sectional view of a moving blade and it moves with a linear velocity equals to u. The steam will enter with a velocity equals to v1 and it makes an angle of alpha 1. So this steam velocity has two components. One is called as velocity of whirl and one is called as velocity of flow. So this one is velocity of whirl and this one is velocity of flow. From the start you have to construct one more arrow which represents the velocity u. The vector difference the velocity v1 and u is called as the relative velocity at inlet. So this is relative velocity at inlet and the angle is here beta 1, that is a blade inlet angle. As the steam will pass over the blade with a velocity equals to Vr1 as an entry, so because of friction some heat will be generated because there is a drop in velocity, and this factor is represented by K and is normally given by Vr2 by Vr1. Then the steam will leave with a velocity equals to Vr2, which is much lower than Vr1. the blade velocity at inlet and the blade velocity at outlet is same, that equals to u. If we join this point with u, we will get the absolute velocity with which it leaves the blade. This angle is called as alpha 2, or this angle is called as beta 2, and this one is V2. This V2 has two components, one is vertical and one is horizontal. The vertical component is called as flow velocity at exit, and the horizontal component is called as velocity of whirl. You notice here VW1 is from A to B, whereas VW2 is much smaller as compared to what? VW1. And the angle made by exit velocity, that is V2, is equals to alpha 2. So the tangential thrust is represented by Ft, and by Newton's law it's a rate of change of momentum. So it is m dot multiplied by VW1 minus of minus VW2, because VW2 is acting in the opposite direction. So this is m dot multiplied by VW1 plus VW2. You have to take the positive sign if the both vectors are in opposite direction, and you take negative sign if it is in the same direction. The power developed is given by, I will write W dot or simply capital P, is equals to the tangential thrust multiplied by the blade speed, that equals to u. So this equals to m dot multiplied by VW1 plus VW2 multiplied by u. Unit of this equation is watts, and the same is the equation for work done, because this is the power developed in 1 second. The diagram efficiency or blade efficiency is given by, or is represented by eta B, is the output power divided by input power. Output power is W dot, input power is given by nozzle in the form of kinetic energy is half m dot V1 square. So this will become 2 times of VW1 plus VW2 multiplied by u, and whole thing is divided by V1 square. The gross or stage efficiency is represented by eta S. So your stage is consist of a nozzle and the moving blade. So it's a product of two quantity, that is called as nozzle efficiency multiplied by the blade efficiency. There is a small axial thrust because of component of Vf1 and Vf2. So by Newton's second law, it's a rate of change of momentum, m dot Vf1 minus Vf2, and the thrust is in Newton. Because of friction, the inlet velocity is Vr1 and outlet velocity is Vr2, and this drop in the velocity is because of purely friction. So we can find out how much amount of energy wasted in friction. So right, amount of energy wasted in friction or heat loss in friction. So that will be given by 1 by 2 in the form of kinetic energy. At inlet we have kinetic energy equals to what? Vr1 square, and outlet is Vr2 square. The friction is taking place over the blade only. The condition for maximum blade efficiency. The blade efficiency is given by 2 times VW1 plus VW2 as referred to this figure multiplied by u divided by V1 square. So before this we'll combine this diagram actually, and this is the common velocity to both figure, that equals to the blade velocity A to B. At this one the nozzle is inclined at an angle equals to what? Alpha 1. So this one is alpha 1, and this one is blade velocity equals to u1. So it has two components. One is velocity of whirl and one is velocity of flow. So this value, let's say this value equals to C, this one is D, this component is VF1 and this is VW1. VW1 is cos and VF1 is sin. Then if you join B to D, you will get the velocity, relative velocity at inlet, and this angle will be equals to beta 1. So this one is your inlet velocity triangle. So when you are going to the outlet triangle, we come across K, and from K we can calculate VR2. So that is the standard procedure to go for outlet triangle, and you have to construct beta 2 at this point. This figure is not to the scale, but in fact VR2 is less than VR1. So this is VR2. Makes an angle of beta 2 here. Let's say this point equals to E point. If you join A with E, you will get the absolute velocity at exit, that equal to V2. And this makes an angle of alpha 2. And this V2 has again two components. One is VW2, and VW2 always act in opposite direction of VW1. And this one is the second component, that equals to VF2. And the point we obtained is equals to F. Now your objective is to maximize this. So first of all, you have to investigate that on which parameters of your blade efficiency is dependent. Whether it is dependent on VW1, VW2, U, V1, or only on the ratio of U and V1. For this one, we take the help of this figure. Now VW1 plus VW2, so VW1 is equals to what? AC, and VW2 equal to what? AF. So is it a full length F to C? So VW1 is from here to here, that is A to C, and VW2 is from A to F. So AC plus F, that is equals to what? FC. Now instead of writing FC in this fashion, can I write this in the form of FB plus BC? But is FB is nothing but, is this FB is nothing but, is it VR2 cos of beta 2? So this is VR2 cos of beta 2. And is BC from here to here, is it VR1 cos of beta 1? Now what we'll do is that we'll take out VR1 cos of beta 1 outside. So this is VR1 cos of beta 1, and I will prefer to write 1 plus, then I will write down VR2 by VR1, and then is cos of beta 2 divided by what? Cos of beta 1. So it can be written as VR1 into cos of beta 1 into 1. VR2 by VR1 is equals to K, and let's say cos of beta 2 by cos beta 1 will represent by uppercase B. B is just a ratio of cos beta 2 by cos beta 1. But if you write the equation this way, there is still no advantage as compared to the equation of what? Eta B, because it does not contain any VR1. So what we do is that we will try to write this VR1 in terms of what? Or VR1 cos beta 1, that is BC. Can we write this term BC as VW1 minus U? And then can we write down VW1 in the form of V1 cos alpha 1, so that my denominator will get cancelled. So VR1 cos beta 1, that is the term BC, will be replaced by VW1 minus U multiplied by 1 plus KB. But VW1 is equals to V1 cos of alpha 1. So this one is V1 cos of alpha 1 minus u multiplied by 1 plus kb. So we'll put this value in the equation of eta b. So eta b becomes 2 times v1 cos alpha 1 minus u into 1 plus kb multiplied by u, and whole thing is divided by v1 square. Which is represented normally by letter rho and is basically u by v1. 1 of v1 can be adjusted in the first bracket, so that will be equals to what? 2. Then this is v1 by v1, is it equal to 1? So it will be only cos alpha 1. U minus u divided by v1, so that is equals to what? Minus rho 1 plus kb as it is. And second value of v1 we will adjust below this u, so is it equals to rho. Now this equation says that the blade efficiency is a function of what? Rho, alpha 1 and k, that is VR2 by VR1, and b, that is the ratio of what? Cos beta 2 by cos beta 1. If this value, that is angle alpha 1, beta 2 are fixed and k is also fixed, then is this equation is a function of rho only. To maximize this, we differentiate eta b with respect to rho, and we'll try to find out the stationary point, which gives the condition for maximum efficiency. So the derivative of this term will be equals to 2 times cos alpha 1 minus 2 times of rho into 1 plus kb. 1 plus kb cannot be equal to 0, but 2 is also is not equal to 0. It means that cos of alpha 1 minus 2 rho must equals to 0. So that is what we have got the condition. Condition for maximum blade efficiency is rho equals to cos alpha 1 by 2. And if you are interested in the maximum efficiency of blade, then you have to put this value in the equation of blade. That equals to what? 2 cos alpha, instead of rho we'll put cos alpha 1. So this is cos alpha 1 by 2 multiplied by cos alpha 1 minus cos square alpha 1 into 1 plus kb. This term is cos square alpha 1 divided by what? 4, and everything is again multiplied by what? 1 plus kb. The solution of this term is cos square alpha 1 by 4. Is it correct? Multiplied by 2. So is it a cos square alpha 1 by 2? Now if we assume the ideal condition, that is there are no frictional losses, so is VR2 by VR1 equals to 1. So what is the value of k? Is equals to 1. And if we assume the blades are symmetrical, then is cos of beta 2 is same as cos of beta 1. So that is also equals to what? 1. This 1 plus 1 will be equals to 2. So is the maximum blade efficiency is simply cos square alpha 1. If we consider this equation of eta b, that is 2 times cos of alpha 1 minus rho into 1 plus kb multiplied by rho. Or you can consider the lower equation 2 times, and if we assume k equal to 1, that is there is no friction and the symmetrical blade, and let temporary the alpha 1 equals to what? For 20. So is the blade equation will become this 2 and this one is 1 plus 1, that equal to 2. So 2 into 2 is what? 4 rho into cos alpha 20 minus rho square. So this time is the blade efficiency is proportional to minus rho square, and is minus rho square is a downward parabola. Is it correct? The above equation represents a downward parabola. So it can be shown like this. On y-axis we have eta b, on x-axis we have speed ratio. If rho equal to 0, the blade efficiency also equals to 0. And it will have a max value at equals to 0.5 as per the given condition. And if you check it, will it be equal to again 0 at this point? What is given to you? A simple impulse turbine. The diameter is equals to what? 30 cm. So D equals to 0.3 meter. The rotational speed is 200 rps. 200 rps is 12,000. Now this data is sufficient to calculate the value of U. U equals to pi dn by 60. Blade velocity will be 188.5. What is the nozzle angle? Nozzle angle is alpha 1 equals to 20 degree. And is the exit velocity of steam from nozzle is the blade inlet velocity? That equals to what? 850. And is the factor K is given to you? How much is K? Loss is 10%. So K equals to what? 0.9. And blades are symmetrical. Does it mean that beta 1 is same as beta 2? So you know the value of U. You know the value of V1. This diagram is drawn without scale. This one is alpha 1. This one is V1. Let we have two components. One is this value, that equals to what? Vf1. And one is this value, that equals to what? Vw1. So this one is Vw1 and this one is Vf1. Out of this, Vw1 is the cos component of V1. So this one is V1 cos of alpha 1. V1 is 850 and cos alpha 1 is cos 20. Similarly, Vf1 is V1 times of sine of alpha 1. So one is cos, other is sine. So this one is VR1 and this angle equals to what? Beta 2. Are we able to find out value of BC? Is the value of BC equals to what? AC minus AB, and BC equals to what? Vw1. Vw1 is 798.7. And value of U is 188.5. So we can calculate BC. So we know the angle, we know the value of BC. Now check, is the triangle BCD is a right angle triangle? So can we apply tan beta 1? So what is tan beta 1? Tan beta 1 is opposite is CD and adjacent is what? BC. Out of that, CD means VF1, which is equals to 290.7, and BC is 610. So you can get the value of beta 1. So VR1 you can obtain by Pythagoras is under root of BC square plus CD square. VR1 is 675.9. Now we'll start the outlet triangle. To enter to outlet triangle, first you have to find out value of K. Is the value of K equals to given as 0.9, and is K equals to what? VR2 by VR1. Two informations are required for outlet triangle. One is relative velocity and one is blade velocity at outlet, that equals to beta 2, which is same as beta 1. Now using this information of VR2 and beta 2, we have to construct one angle here equals to what? Beta 2. Figure is not to the scale. This one is beta 2 and this one is VR2. Now you have to join the point A with this point, and that will give the value of V2. Let's say point equals to what? E. Extend this point on the left hand side and draw vertical through this point. to complete the triangle. Let's say this point equals to F. The distance between A to F is VW2 and distance from E to F is VF2, and this angle equals to alpha 2. To find out the value of VW2, we'll use the cos beta 2. So what is cos beta 2? Cos beta 2 is adjacent, which is sum of what? U plus VW2 divided by VR2. Beta 2 is same as beta 1 and U is equals to 188.5, VR2 is equal to 608.3. So you can calculate VW2. Then you have to use one more, that equal to what? Sin beta 2, and value of sin beta 2 is opposite, that is equals to VF2 divided by VF2. So you will get the value of VF2, 261.6. Apply the Pythagoras now. So what is V2? So V2 square, or V2 equals to under root of VW2 square plus VF2 square, 445.5. Okay, is the blade efficiency is given by 2 times of VW1 plus VW2 multiplied by blade velocity U divided by inlet velocity square. Answers are like this. The blade angles are beta 1 equal to beta 2 25.47, blade efficiency is 60%, and absolute velocity equals to what? 445.5. If they will ask you the specific steam consumption, that can also be calculated. Specific steam consumption is simply given by 3600 divided by specific work. Specific work is given by VW1 plus VW2 multiplied by U. M dot will not appear. Specific fuel consumption is mass of fuel multiplied by 3600 divided by what? Brake power. Now this time what we have done, in a specific steam consumption we are using 3600, and is a brake power divided by mass flow rate is a specific quantity, that is a specific work done. So this equals to W net. But remember, the unit of this quantity is kg per kilowatt hour. So there is a conversion required here, that this value should be divided by what? 1000. So that it will come in kilowatts. So 16.47 kg per kilowatt hour.